Right, so we're starting a new chapter today, Planarity. I have a love and hate relationship with this chapter. I'll tell you why it's important, I'll tell you why it's nice, and yet the details are terrible. And it's also important to be able to do the terrible details. So this definitely has a place in this course. In the exams, I won't be asking you to reproduce these very detailed proofs, like can you prove lemma 4, 5, 6 or something, but I might ask you sort of little arguments. Why is, I don't know, why are these two faces of a plane graph different, distinct or not, and so on. So you need to be able to master the terrible little arguments that I'm going to inundate you with today. But before we get there, why is it important? Well, one historical reason is that this is how graph theory started, or sort of one of the sources. Euler is claimed as the bridge problem is claimed as one of the origins. Another is the four-color theorem. Right? You remember the map coloring problem from the first lecture? So the four-color theorem now says that any graph that formalizes such a map can be colored with four colors, vertex colored with four colors. So every map can be colored properly with at most four colors, where properly means adjacent countries get different colors. This has been translated into a vertex coloring problem for graphs, namely the graphs that represent these maps. Every country becomes a vertex, and two countries become adjacent if they share a boundary. And so it's not true that every graph is four-colorable, vertex colorable in this sense. We haven't got there yet, but that'll be the next chapter. So there must be something about these graphs that come from maps that sets them apart from other graphs. And what exactly that is, well, they can be drawn in the plane without edges crossing or something. And this chapter is about making that precise. So it has a historical origin. More importantly, I would say, this kind of topology, point set topology in the plane or in other surfaces has a place in graph theory whether we like it or not. And the best example is quite a recent example, something like 20 years ago, the big structure theorem for graphs not containing a given graph as a minor. So you know what graph minors are, and classes or properties formed by forbidding one or more graphs as a minor. So a property of the kind, all graphs that don't contain this particular graph as a minor, as a subgraph, whatever you like, those are very natural properties, and they occur all the time. And in particular, given any graph, those not containing that particular one as a minor have been characterized. And this characterization, depending on that graph, if it's a large graph, for example, a large complete graph, necessarily involves surfaces. We can't escape that. So there's a very complicated structure theorem that involves surfaces, embeddability of graphs in surfaces in an essential way, and there's no way around it. So these surfaces, or embeddability in surfaces, just comes up as the solution to a problem rather than as a toy example of what we might be interested in, like the map coloring. So it's not people that say, oh yeah, I love surfaces, let's put some graphs on them, but it's people that said, I like graphs and I want to study natural graph properties, like not containing that K17 as a minor. And then they worked for half a century and came up with the structure theorem, that's Robertson and Seymour, that involves embeddability in surfaces in an unavoidable essential way. So embeddability in surfaces, and in particular in the plane, in the Euclidean plane, does play a role whether we like it or not. So we have to come to terms with it. And the purpose of this chapter is to teach you a rigorous way of coming to terms with them so that we'll never have to visit these slums of topology anymore after this chapter. But you must be able to do the hard work. I mean, not hard work, but the sort of the details. And I want to put you in a position to be able to do that. So here's a way of not to do planar graphs. You know Euler's formula, perhaps. That in a plane graph, the number of vertices minus the number of edges plus the number of, we call them faces, so regions of the plane minus the graph is always true. So that's in a connected graph. That's been drawn in the plane in such a way that edges don't cross. And if you, I don't know, I haven't done it, but I suppose if you go to Wikipedia or something and you look this up, you'll see the following proof. You'll see an induction proof that goes roughly as follows. Here's your plane graph. And you say, okay, pick an edge, this one, delete it, and apply induction. So after deleting the edge, M has gone down. But so has F, because these two faces merge into one. So we can apply induction. The sum is 2, and after adding 1 and subtracting 1 again, will remain a 2. End of proof. Yeah, it sort of looks natural, and you might ask, where does the induction start? Okay, I don't know. We're connected, so let's start at trees or something. Yes?
Sorry, what are faces here?
Precisely, very good question. What are faces? You asked what are faces. I said they're the regions of the plane minus the graph. So that's a face, and that's the face. But you're hitting the point. Why isn't that a proof? Because we're not involving the definition of the terms of the assertion. Why are we not involving the definitions of the terms? Because we haven't given the definitions. We haven't defined anything. I've been sort of waffling about pictures. This is not mathematics. In order to turn it to mathematics, well, it's a bit like this modeling story that we had recently, but it certainly is if you want to apply it to printing maps. But we'll be defining plane graphs, graphs drawn in the plane properly, and then we'll define such things as faces properly, and then we'll prove this. Not today. We'll have to get through lots and lots of terrible details today before we even get to the proof of that such a simple assertion. Okay, so let me just give you a very quick list of what we'll assume. And what I sort of, there are three categories. One is notions that I assume that you know, and you can look them up. You really ought to know them. Then there are statements which I'm assuming to be true. phrased in terms of these notions, so you can understand the statements, but you don't know why they're true. And I'm not telling you why they're true. I'm telling you that they're true. And when I wrote this chapter 100 years ago, I tried to minimize the list of these statements. So there's something like 3 of those that I need to be able to assume without proving them as a basis for everything else, such as a proof of Euler's formula. So that's the second thing. And then from there on, everything will be precise. And I challenge you to challenge me for gaps. If you find an argument not to be precise, do say so. And try and catch me, please. And then I'll make it precise, or I'll say, well, I wish I could. One of those. And we'll end up, I promise, we'll end up making it precise in terms of these terms that, definitions that I assume that you know. So the first is, well, you need to know what a topological space is. You need to know the topology of the plane. And you need to know the subspace topology of subsets of the plane. So that's simply the intersections of such a subset with the open sets in the plane. They form a collection of open sets for that particular subset. So that's the subspace topology. You look it up if you're unfamiliar with it. Then I need the notion of the frontier of the subset of the plane. Yeah, and the definition of that is simply you have your subset somewhere and a point. It doesn't matter whether it's a point of that subset or not, with the property that every neighborhood, open neighborhood of that point, meets both x and the complement of x, r minus x. Such a point is, the frontier is the set of all those points. Right? That's the definition of frontier. And you can prove that the frontier of a set is always closed. Right? Why is it closed? So if you have to show that the complement of that frontier is open. So for every point in the complement that's not on the frontier, you have to show that it has an open neighborhood that is entirely, that misses the frontier altogether. But that's easy, right? So if you take a point that's not on the frontier, why is it not there? Because it's not true that every neighborhood meets x and the complement. So it has a neighborhood that only meets x, or it has a neighborhood that only meets the complement. And you can take that neighborhood as an open neighborhood of that point, all whose points are in fact outside the frontier. So that's a quick proof of why frontiers are closed. And so in particular, if x is open, not in particular, if x is open, then yes, then the frontier is entirely outside x. Right? Why? Because if x is open, then every point has a neighborhood that's entirely inside x. That's the definition of open. So in particular, it has a neighborhood that doesn't meet the complement of x, so it can't be on the frontier of x. So if x is open, then the frontier of x is entirely outside x. Then for true points, x and y in the plane, I need something that I call a straight line segment. So what's that? That's something like the set of all lambda x plus 1 minus lambda y, such that lambda is between 0 and 1. Right, it's a particular set of points. X and y are points in the plane, and that's another particular set of points. It's we call it the straight line segment between x and y. You've seen it in linear algebra. Why is it straight? Bad question. There's no definition of straight. We call it straight because that's the way we view the plane, so that whenever we put all these points there and ask our computer to plot these points, they look straight. That's the reason we call it a straight line segment. There is no proper mathematical reason. That's the definition of a straight line segment between x and y. Such things are homeomorphic to the interval 0,1, the real interval 0,1. And when I say homeomorphic, I mean I'm referring to the subspace topology of this set of points. Right? So what's an open set of this? It's an intersection of an open set in the plane with this. So that's an open subset of that set, for example. Okay, and more generally, subsets of a plane that are homeomorphic to 0,1 are called arcs. I call them arcs. Right, there's some, not to be confused with what topologists call paths. What topologists call paths are continuous maps from 0,1 to a space. They may self-intersect, right? So these continuous maps needn't be injective. Sometimes they are injective, then they speak of injective paths. And the image of an injective path is then homeomorphic to 0,1, and that would be an arc. But my point is that an arc is not a map. It's a set of points. It's a subset of the plane. Okay? So let me write it like that. And this is polygonal or piecewise linear if it looks like this, no, without dots. If it's a finite union of, yeah, let's say finite, union of such straight line segments. So what's a polygonal arc? Two requirements. It must be a union, finite union of such straight line segments, of sets of points of that type. That's the first requirement. Second requirement, the entire thing must be homeomorphic to 0,1. So if I add another straight line segment like this, that's no longer an arc, a polygonal arc. Right? So, but it's an arc, and it's made up of straight line segments. And then there's also something called a polygon, which is a finite union of straight line segments that's homeomorphic to the unit circle rather than to 0,1. Okay. So if x is finite union of straight line segments, then in particular X is compact. So you ought to know the definition of compact. For subsets of the plane, it happens to be the same as closed and bounded. That's not the definition. It's true for these particular sets. You need to know both. The fact that they're the closed and bounded subsets of the plane, but you also need to know the definition of compact, namely that for every open cover you can select a finite subcover. So why is such a finite union of straight line segments compact? Well, because the straight line segments themselves are compact as homomorphic images or continuous images of Nord 1. And Nord 1 is compact. Yeah, that's easy to prove from the definition of compact. And so finite unions of compact sets are compact, and so such an X is compact. What I want then for such X, then means for these particular X, right? Then a region of R minus X is an equivalence class with respect to, let me just draw that rather than say it, rather than write it. So if X is yellow and we have our finite union of straight lines, then a region of the complement in the plane is an equivalence class with respect to being linkable by a polygonal path entirely in the complement of X. So that's clearly an equivalence relation, right? So if this can be linked to that, that means if this appears as the image of naught and the other as the image of 1 in this homomorphism, which exists for every arc, in particular for a polygonal arc, then also the other way around they're also linked. And if you have one to the other and that to this, then there's also an arc from here to there, still polygonal. So transitive is also clear. So that's an equivalence relation, and the classes are called regions of this complement of X. And they're open. Right, because X is closed and bounded. So can you prove that? Why is a region open? Well, plane minus X is open because X is closed. So plane minus X is open. Why is the region open? Well, take a point in the region, and we want to find a little disk around it, open disk around it, that's entirely in that region. Well, choose a disk that's entirely in plane minus X, and that exists because plane minus X is open. And notice that this disk consists of points that are pairwise equivalent. Inside that disk, you can join every two by a straight line. That doesn't hit X. So they're all in the same equivalence class. So this particular little disk also shows that whichever region point that we chose was in, like the entire disk is in that particular region, so this region is open. Okay. Last little observation or fact that we need. So when we have an open set, call it O, and then that's an open set in the plane, and then we have the complement I think I want. Yeah. So then here we have the complement, and the assertion now is that the frontier of O separates, not in the graph sense, separates O from the complement. And in which sense then? In the sense that every polygonal arc from a point in O to a point outside O has to hit the frontier of O. That's sort of, if frontier was an even moderately fitting term, then that should be true, right? So when you leave a room, you have to go through the door, right? But so, why is that true? We can show even more. So I want to, this is an arbitrary polygonal arc from a point in O to a point outside O. And my claim is that this particular polygonal arc has a first point, has some point, but in particular has a first point on that frontier. What does that mean? What does first mean? Don't say, well, you don't get to another point before that, unless you can back it up by a definition. So what does first mean? No, not of distance, of before and after. Yeah?
But if we walk a path, we start somewhere and we end somewhere, if we if we choose a path between two vertices and start with one vertex and then just say, okay, the first one is
No. So we're not in a finite graph here. Right? So the question is really, could it be that this maybe does hit the frontier, but it hits it sort of on the way here. I've had, oh, this lies on the frontier. Maybe that does too. Oh, that does too. That does too. That does too. Maybe there is no first hitting point. So what does first mean? First, obviously, has to involve the definition of P. What's the definition of P? It's something homeomorphic to this. What is so there is a homeomorphism from this to this yellow set of points that maps 0 to that point and 1 to that point. And by a first point in some set, I mean one whose parameter lambda is, or here, is minimal. Not here. We're not talking about straight lines. Right? We're talking about this homeomorphism from 0, 1. So I'm looking for a minimal set little lambda in node 1 with a property that lies in the frontier of X. And that might or might not exist. So it does exist. Proof? we have to work now in this parameter space, in this interval. And the proof is, well, consider as lambda the supremum of all points little x in 0, 1, such that the entire interval from 0 to this x is still inside O. Once more. The suprema exists, minima needn't exist. But the supremum exists of all points little x, such that the entire interval from closed interval from 0 to x lies inside O, as a subset of O. And if you call that supremum lambda, then you can prove that lambda lies, that the image under this homeomorphism is on the boundary of x. Right. Why does this homomorphism map this particular supremum of all these little x's such that this interval maps to O, to the boundary of this? Well, we have to show that every open neighborhood of this point hits x and the complement of x. So let's use continuity and go back to an open neighborhood of this lambda that maps into this open neighborhood there, which exists by continuity. And then you know that all these points here must be in x. If one of them wasn't, then you find a slightly bigger one, such that this interval here doesn't lie entirely in x, doesn't map entirely to x. So all these points before lambda, no matter how close, have to lie in x. If you find one, no matter very, very close, that doesn't map to x, take one even closer, and then this closed interval doesn't entirely map to x, contradiction to the definition of lambda as the supremum of all these things that do. And similarly for the outside. Right? So that's the sort of proof you ought to be able to do yourself. I'm not going to bother you anymore. I'm going to torment you today with proofs of that type, but only today. Promise. Okay. Questions? No. So that was what I need as elementary facts that you ought to be able to prove from definitions you ought to know. Now, some facts that I'm telling you are true and you don't have to be able to prove. And the first of these is the Jordan curve theorem. And the Jordan curve theorem says two things. It says that if you have a closed curve in the plane, let's take a polygon in the plane, right? Closed curve is anything homeomorphic to S1, but let's stick with polygons. If you take a polygon, then the plane minus that thing, so let's call it C, then the plane minus C has exactly two regions. I'm tempted to say here and there, but here and there are neither here nor there, right? So they're undefined, obviously. the existence of two and only two regions of this point set is claimed by the Jordan curve theorem. And it claims one more thing. It says that every point of C lies on the frontier of both these regions. Right? So there are two regions, exactly two regions, and every point lies on the frontier of both. Those are two facts that are that together make up the Jordan curve theorem, and it has an easy direction, and it has a harder direction. The easy direction is that there are at most two regions. And the way you prove that is, well, you take a point and you go a little bit to the right, and then you follow this round until you get back there. So by follow round, I mean you stay within, I don't know, you cover all this in little disks that, since we're polygonal, meet the entire C only in the little straight segment that contains them, or the two straight segments that contain them. And then you can sort of wiggle your way through there by a connecting arc that shows that this point is equivalent to everything here, and from anything in here you can get there as well, unless by some magic you don't arrive here but you arrive there. Then you can't close up. Then you might be doing the same thing here and then arrive here. In which case you'd have only one region. Well, that's clearly unreasonable, isn't it? Or not? Can you imagine that? Can you imagine that happening? So that's the harder part, that there is indeed two distinct regions, not just one. At most, one follows from this argument. If you go around, at most, you may have to do it twice, but no more than that. So why is there only? So is it imaginable that there's only one region? Yeah. Take a Mobius strip. So take a strip and take the middle of that strip. So if you take the middle of that strip as your C, and you go round at the top, you end up at the top. If you go round the bottom, you end up at the bottom. But if you cut it here and then do that and glue it back together, then if you go around the top, you somehow arrive at the bottom. And then you go round and arrive at the top again. So sort of you can make a model where all these shaded points are in the same region. So C lies on the boundary of only one region. Yeah, so it is possible in principle, and the Jordan curve theorem has this history of being overlooked for a long, long time until I think it was Jordan who noticed that there was something to prove. People thought, oh, well, it's clear. Draw a circle in the plane, and obviously you have two regions. Well, I try to shoot down the obvious by giving the Mobius strip. Now, the plane doesn't contain a Mobius strip, but why not? Will it prove it? Right, so there is something to be proved there. There are now combinatorial proofs, especially for polygonal arcs, that are not that hard, and some quite ingenious and nice, but that's not our topic, that's not graph theory, so I'm just telling you that, and won't elaborate any further. That's the Jordan curve theorem. Second statement I'm telling you, that is 4, 1, 2. That's what I call the theta lemma. So you have 2 points in the plane joined by 3 arcs that pairwise meet only these 2 points. Say P1, P2, and P3, then the first statement is that the plane minus those 3 arcs has exactly 3 regions, and that each of them are bounded by a circle, believe it or not. This is bounded by a circle, yeah, we would have thought that. You need the Jordan curve theorem to prove that. All right, so it has exactly 3 regions, the complement, and each of them is bounded by a circle, namely which circle? Well, the circles that are the unions of 2 of those 3 arcs. And then there's another assertion, and that is if I take a path across here, then it hits the 3rd path. I tried hard to phrase that in a wishy-washy sort of way. What does across here mean? Well, okay, so you take a point in the an inner point of P1, you take an inner point of P3, and then you choose an arc from that, the first point to the second point. Where? Well, you don't have to choose. I'm telling you, if you have an arc from here to there, and I said that goes through here, well, it goes through one of the 2 regions of plane minus the union of P1 and P3, which by Jordan does have 2 regions, and it goes through one of them. Which one? Well, the one that contains the interior of P2. Why is the entire interior of P2 contained in one region of the plane minus P1 union P3? Well, the reason is that the inner points of P2 are all pairwise equivalent. P2 itself is a polygonal arc, so any point in here can be linked to any point and the other point in there by a polygonal arc that doesn't hit this circle P1 union P3. So they're equivalent by definition of equivalence in plane minus P1 union P3. Okay, so the inner points of P2, they all lie in the same region, and that is one of the 2 regions that I'm assuming the blue arc lies in. And then if it does, the lemma claims that it meets P2. It can't sort of somehow dodge P2 on the way from left to right. That needs the Jordan curve theorem to prove, so, which is my excuse for not proving it. And then the last statement that I want to tell you is basically that if you have less than a circle, if you just have an arc, then that doesn't separate the plane. So plane minus 1 arc has only 1 region. And we need it in a slightly more general form, that is, that if you have what in the applications are going to be 2 disjoint graphs, but now there are 2 compact sets, x1 and x2, compact and disjoint. So rather than assuming compact, let's assume that they're a finite union of straight line segments, and therefore compact. And then the assertion is, well, we have to be a little more careful of how to phrase it now. Let O be the region of plane minus x1 union x2 that contains the inner points of P. Right, the inner points of P are pairwise equivalent in plane minus x1 union x2 because they're connected by arcs that entirely lie outside x1 union x2. So they're all equivalent. So the entire interior of P lies in some region of plane minus x1 union x2. Call that region O. Now add P to x1 and x2. And the assertion now is that O minus the interior of P is now still one region only of the plane minus x1 union x2 union P. So this doesn't sort of separate the face that contains it. Okay. Now, just to give you, to alert you to the fact that there is something non-trivial going on here, I told you that x1 and x2 are compact. In fact, we're assuming that they're like this, but all I need now is that they're compact, so closed and bounded. Can you tell me a counterexample to this statement if we don't have closed or if we don't have bounded? So if x1 and x2 are closed but unbounded, can you find a counterexample where this P does split the region that contains it, the region of plane minus x1 union x2, into two regions of x1, plane minus x1 union x2 union P? Here it is. x1, x2. Two straight lines parallel to each other, going to infinity both ways. And then take this as P. Right? P goes through a region O of plane minus x1 union x2. But then when you look at what this O minus P isn't one region of plane minus that union, that union, that. Right? These two things are no longer equivalent, the points in them. So that's a counterexample when you drop the bounded requirement, and a counterexample for dropping closed, but where you have where you are bounded is this. So take a little circle. Take this as x1, that as x2. These are big x's. And x1 is homomorphic to an open interval at 1. And x2 is an arc, so homomorphic to a closed interval not 1. And if you put this P there, then you've split this face of plane. What is plane minus, what is union x1, x2? That's exactly this circle. So plane minus that has two regions by Jordan. And if you let P link two such points, as in the theta lemma there, then it does split the region it goes through into two regions. Yeah. I mean, there's no algorithm for coming up with such examples. And it's quite something if you even notice that there's something to prove. And that is really what I want to train you at here. Okay. I think that's all. One example where this is applied is that trees have a complement that has only one region. Right? And you can prove that, I don't know, by induction on the number of edges or something. Right? So, and we're going to use that and need it later for our proof of the Euler formula as the induction start. That trees leave only one region, right? Trees have one more vertex than edges, and there's one face, so it works for trees. Yeah, but you need that there's only one face. There's only one region. Okay. Right, that's all for preliminaries. Now, let me tell you what plane graphs are. There's going to be two things, plane graphs and planar graphs, that we'll have to distinguish. And plane graphs are essentially point sets of points in the plane, and planar graphs are real graphs, abstract graphs, that are isomorphic to some plane graph, which we then abbreviate as saying can be embedded in the plane. So let me tell you what a plane graph is. It's a pair, it's not quite a pair of points, but essentially. So it's a pair of two sets where the they're both finite. So V is just a set of points in the plane, any set of points. E is a set of polygonal arcs. With a following property that they don't have inner points, these polygonal arcs, that are on other plane edges, as we call them. The elements of big E are called plane edges. So this is not allowed, neither is that. So one of these polygonal arcs is not allowed to contain, as an inner point, a vertex that is not one of its endpoints. Well, it's not allowed to contain its endpoints as inner points either, but Right. So basically, you have a set of points, you call them vertices. Then you have something that we call plane edges. They're just arcs linking those vertices in such a way that they don't cross. Right? So when you have such a thing, it gives rise to a real graph. And which real graph? Well, the graph with vertex set the same v. And what's the edge set? Well, the edge set for every little e, which is an arc, you take the set of its two endpoints, which are, by requirement, elements of big V, and distinct elements of big V. Oh, there's also a requirement that we for every 2e, we don't have the same pair of endpoints, so we don't want multiple edges. Okay, so the formal thing is in the book. My main point here is that, yes, a plane graph is formally a pair of two sets, but then we'll usually identify it with sort of linguistically, with one or two things, either with a graph it gives rise to, where for a little edge we think of this pair, or with a set of points in the plane that are the union of all these sets, of this set and all these little e's. Okay. Oh, yes. And the regions of, I think I want to say of G. No. The regions of plane minus G, and when you see this set minus, that's an alert to telling you that the G that comes after it is a set of points. Right? When I want G to mean a graph, then I write minus. So whenever you see the backslash, then there are 2 point sets. So the regions that are left by taking out such a point set, which is a plane graph, are called faces of this plane graph G. Right? So we speak of regions of the complement, but faces of G. So a face of G is a set of points in the plane which is disjoint from G, namely a region of the complement. Okay. Note that the frontier of any face of G lies in G. Right, so a face in G is a region of the complement in the plane. Frontier points of this region can't lie in another region. So they have to be in G itself. Right, so the formal proof is that such a region is open, right, because G itself is closed and bounded. So the region of plane minus G, which is a face of G that we're considering, this region is open. So the frontier of this region, or the face of G, lies entirely outside it. Right? Remember, open subsets of the plane have a frontier outside that subset. So where can such a frontier point be? Well, it can't be in another region because that's open too. So it would have a little neighborhood that doesn't meet this. So the only place where these points can be are on G. And we'll see later today where exactly on G they are. So for example, whether the frontier of a face can be half an edge. Cannot, but we'll have to prove that. Right. So let's consider a subgraph of G. G is a plane graph. Then every face f of G, of G is contained in some face f prime of H. Right? So let me give you a drawing. Yeah, maybe like this. So this is my G. And maybe the subgraph H is this. Now, if I take a face of G, this little f, that will be contained in some face of H, right? F is this. F prime is going to be the entire outside here, everything except that. All right? And 2 is, if it so happens that the frontier of F, which we know lies in G, right? If that happens to lie in H, so if we're here, the entire frontier, a set of points in G, happens to, all of these points happen to be in H, then this F prime, that is a superset of F, face of H, is only F. Okay, that's all I want to say. So I showed you a proof of the first statement. That's easy, right? No, I haven't shown you a proof, but it's still easy. So why is there a face F prime? Well, F is a face of G, so that's an equivalence class of points of plane minus G. These points are still equivalent in plane minus H because H is a subset of G. So this equivalence class of plane minus G expands to some bigger equivalence class of plane minus H. So that proves this, and that bigger equivalence class is F prime. And why is 2 true? Well, if you have F and F prime is bigger, then you can take a point in F and a point outside F, but still in F prime, and join them up by an arc in F prime. This arc has to hit the frontier of F because it connects a point in F and a point outside F. That's our earlier, this first point thing. There. And this point here is an inner point of F prime. And it's on the frontier of F. But then that's not true. So we're assuming that the frontier of F lies entirely on H and doesn't have a point in a face of H. Okay, so that's the proof of 2. Questions? Okay. Right. Now let's prove that the boundary, I'm not allowed to say that yet, the frontier of a face isn't half an edge. So that's lemma 422. For every edge in G, a few things happen. The first is that for every face F of G, either the frontier of F doesn't contain an inner point of E, or it contains the entire interior of E. Right, so in particular, the frontier of F cannot be half of E. Right? That's not sort of totally inconceivable if we have a face and we have an edge from here to there, some polygonal arc. So this might be something like this, right, where somehow these get so close that we can't get out by an equivalence certifying or witnessing arc. That's not the case. The reason it isn't the case, sort of very broadly, if you were topologists, I would say that's because this is compact. But we have to somehow prove it. Right? You can't get out. The frontier of F, we know is a subset of G, but it can't be like half an edge. Slightly more generally, we prove that if you take any F and look at its frontier, if it meets E in any point at all, in a point at all, that it contains the entire interior of E. Then if E lies on a cycle, then E lies on the frontier of two faces. And if not, then G lies on the frontier of exactly one face. Okay, so let's try and prove that. So E is some edge, say, from U to V, and for every little point in the inner point of this edge E, let's choose a little open neighborhood that meets the entire graph only in the straight line segment that contains that inner point, or if it's at such a vertex of this polygonal arc, then it meets only the two adjacent straight line segments. Right? Why is that possible? Well, because the union of all the other edges and vertices and all the other straight line segments, that's one of those things. Right? So that's closed, and I can find a point, an open neighborhood, a little open disk. I want an open disk around this point that isn't on that set, that avoids that set. So let's pick any point little x naught, and let's call this dx naught. And in the same way, for every other x, we have a d little x. Okay, so let me draw that a little bigger. Now, this, as you can clearly see, is a disk. It's a little egg shape, but don't worry. So this minus that straight line has two regions, this and that. They are contained in regions of G, because this is a subset. No, they're contained in regions of G because these points are pairwise equivalent. They're pairwise joined by a straight line. That doesn't meet G. So this is this here is a subset of some face F1 of G. And this here is a subset of some face F2 of G. And we don't yet know whether F1 and F2 are the same, but what we do know is that this point cannot lie on the boundary of any face other than F1 and F2, right? Because it has little neighborhoods, for example, this dx naught, that do not have, that doesn't meet both that third face and its x and its complement, because it only meets its complement. It only meets the union of F1 and F2. All right, so let's assume that E lies, this entire edge here lies on a circle in G. Then this circle in G is a polygon in the plane. So by Jordan's curve theorem, by the Jordan curve theorem, this polygon has two faces. And every point on the polygon lies on the boundary on the frontier of both. So these points here lie, they're all equivalent in plane minus that circle. these are all pairwise equivalent in plane minus that circle. So these lie in a region of plane minus circle. These also lie in a region. And since this neighborhood here meets both regions, they have to lie in different regions of plane minus that circle. Then they also have to lie in different regions of plane minus that graph G by this, because the circle is a subset of the graph. So the faces of the graph are contained in faces of the subgraph of the circle. And so if F1 and F2 were the same, they couldn't lie in distinct faces of C. So that proves 2. And 3 is basically this. So if E does not lie on a circle, then E is a bridge in the graph, and it separates, now in the graph sense, its two n vertices. So in the plane, E is a polygonal arc between two graphs, between two such sets that are disjoint, and therefore this is only one region, and here F1 and F2 have to be the same. And now we have shown something very local for this little disk around x0, and we have to somehow transport that to every other little x. But that's not difficult, because we just take the set of all these little dx's, one for every x on the entire edge, and I think I want one for every inner point of the edge. Let's continue many little disks. Every disk with this property that I gave you as the definition of dx, so it doesn't meet G elsewhere. Now, this is compact, so we can find a finite subcover of these. We can find finitely many such disks covering it. And then so here was our little x0. We can prove that this was in F1 and this was in F2. Then the same is true for every little x. So this also has one half of this disk in F1 and the other half in F2. And so does this. And we can tell which is which. Sorry, in one phase, not F1 and F2, in one phase and in another phase. But we can get to, for every little x, we can get to our original, from our original dx0 to dx by finitely many straight lines, always staying in adjacent disks. So you have two adjacent disks, you go from here to the intersection. There has to be an intersection because the disks between them cover the entire edge. So you go from here by a straight line to the intersection, then here by a straight line to something here that sees the intersection again, and so on. Right? When you have this, you can't go from here directly there. Oh, yes, you can. Yeah, okay, never mind. So And in this way, you can show that if the points in this disk minus E lie in two faces of G called, say, F3 and F4, then one of those two must be the same as F1, and the other must be the same as F2. So the same pair, F1, F2, crops up everywhere. And that shows that for every F, either the interior of E doesn't meet the frontier of F at all, or the frontier of F contains the entire interior of E, namely that happens when F is one of those two, F1 and F2, possibly they're identical, and that happens if F is any other face. And that's the end of the sort of very, very elementary proof of that. But this is the kind of argument that you have to be able to do yourself all the time, that I'm not going to do for you anymore, but maybe it's good to know how to do it. Questions about that? No. Okay, then. I'll give you two more little lemmas. No, three more. So 4 to 4. Plain forests have exactly one face. Right, and the proof is by induction on the number of edges from this. Right, so proof trees have only one face, and if you take two disjoint trees, then obviously that one face remains one face. So important the frontier of every face is a union of entire edges and vertices. Right? The frontier contains some vertices, fine. Maybe there's some isolated vertices somewhere that lie on the frontier of a face. If anything more lies on the frontier of that face, it'll be an inner point of some edge, and then the lemma says that the entire edge lies on the frontier of that face. So the frontier of a face is a plane graph. It's a subgraph of G. And that we now, at long last, call the boundary of that face. Now I'm allowed to say boundary. So boundary is a graph. Frontier is a set of points. Okay. So that's important to remember. Face boundaries are subgraphs of the graph whose faces they are. Question, can two faces have the same boundary? Yes?
I would say yes. It's just one.
You're saying yes? It's clearly impossible. But carry on. Yes, carry on.
Like if we just have one surface.
Yes, precisely. Sorry, I try to... No, of course. Yes, if the graph is a cycle. Right? Yeah, good. Are there any... There was a colleague in Cambridge once who was sort of a very imposing figure. He was a behaviorologist, he was not a mathematician. Very imposing figure and a very, very kind man. And it so happened that he was told one day by a friend, the friend said, look, I've heard it said that you can at times be intimidating. He said, what, me? I'm so nice. I'm not intimidating. I can't be. Well, maybe ask your students, I don't know. So he goes back to his class and says, I've been told I can be intimidating. Hands up who finds me intimidating. So, yeah, apologies for that. Okay. Can any other graphs have faces with the same boundary? So the claim is now, if that's the only example, that if a graph has two faces with the same boundary, then the entire graph is a cycle. Not just the boundary of that face is a cycle, but the entire graph is a cycle. And the answer is no. It really cannot happen. Can you prove it? And the answer is also no. Well, probably not, but it's damn hard to prove. So the way all these silly lemmas came up was that this is where I got stuck when I wrote this chapter. So I wanted to say, yeah, I mean, obviously two faces, I needed somewhere that two faces can't have the same boundary. And then I thought, oh, why is that true? And I tried to prove it, and I sort of noticed that I needed things like this, or like that, and so on. No, the proof of this needed that, and needed Jordan, and so on. So all these lemmas that I've told you so far, I think, occur in the proof of this elementary little fact that the cycles are the only plane graphs where two distinct faces have the same boundary. The proof is not long on the basis of all this nonsense here. Right? So it's about, I don't know, 10 lines or something, but I won't walk you through the proof because it's really, really formal, and I invite you to not read it just yet, but to think how you prove it. Maybe you are now sufficiently prepared. I think you are, that when you have all I told you so far at the back of your heads, then you probably can prove it. But do try. Give it like 10 minutes or something before you read it. Yeah. But the reason the proof is so unintuitive is that it's completely hypothetical. You have to start with a graph and assume that two faces have the same boundary. Well, how do you picture such a thing? You can't, because it's not true. So it's very difficult to sort of think of such a face here going to the same, having the same frontier of another face, and so on. So one really has to use the definitions, obviously, and all these facts. So I'm not going to prove it to you. Try to do it yourself. And then when you're done, please read it in the book. Okay, and the last, no, I'm out of time. So the next statement is something I'll start with on Tuesday, and that is in a two-connected graph, every face is bounded by a cycle, but that's already beginning to look a little more like graph theory. So we've gone through the slums of topology today and won't need any more. Maybe a little more in the proof of just that, but that'll be it. And then we'll do plane graphs next lecture. Again, I look forward to that.